Hello, this is Bryan Vakiner, and here is my video for Lab 2, Motion of a Falling Object. The objective of this lab was to analyze the motion of a ball as it is dropped from rest. Then we were to model the observed motion with and without drag. As shown here, I used a juggling ball and I dropped it from a height above my head until it came to rest on the floor. From this, I obtained my time and position values that I plugged into a spreadsheet in order to graph my model versus predicted. But using this information, I created the lab code modeling it without drag. I weighed the mass of the ball, came out to 83.2 grams, so I plugged it in as 0.0832 kilograms. The position is initially 0 and the velocity is initially 0, as is the time. Chose delta t to be 0.001 seconds because the duration is for 0.053, which 0.053. G is equal to 9.8, J hat is that, and for this one we are discounting drag, so the proportionality constant B for the magnitude of drag force is equal to 0. Down in this portion of the code, as you can see, I manipulated it and solved for the weight force. Here's the drag force equation, which in this model of the code is negligible, does not matter because it will end up being 0. F net is, of course, the sum of all of the forces. Here's where I use Newton's second law to predict the final velocity, or predict the changes in velocity, and then I use the position update function here to update the position of the ball as it fell. We go ahead and run that. As you can see, there's the weight vector. There's no vector going up because the drag force is not involved. Gives you a parabola going down, which eventually straightens out. And as you can see here, this is it modeled against the experimental and model position for no drag. As you can see, there's a little bit of a discrepancy. The experimental position went a little bit further than what the model was saying. I think this has to do with the fact that it was a little bit more massive than what you might expect for an object falling like this. So again, once I did that, I rewrote the Python code to account for drag, got a proportionality constant of 0.0013. Go ahead and run that, and as you can see, very similar. Went ahead and modeled that against the same data I received in Tracker, and it gets a little bit better, corrects itself just a little bit. I feel like the discrepancy still is that the weight force is very, very negligible due to the mass of the ball. Here again is another look at the physics that is involved. Newton's second law, the position update, the drag force, and the gravity. We asked to discuss does it mean, examine the velocity versus time predicted by your models with and without drag. Which models, if any, predict a terminal velocity? Discussed briefly. The only one that would predict terminal velocity would be the model with the drag. Terminal velocity is whenever the weight force is equal to the drag force and the object ceases to accelerate. That's why the graphs eventually will straighten out in their slope. What if, imagine that the object was initially thrown downward, would the terminal velocity in this case be the same or different? The terminal velocity will not change. The terminal velocity is constant for every object. Throwing it down initially will just help it reach its terminal velocity quicker, but the terminal velocity itself will not be any greater. So once again, took a video of me dropping a juggling ball and plugged that data that I got into a VPython code to model it against the model and experimental outputs. That's what you get, and I hope you guys enjoyed that and hope that was informative. Thank you.